problem on my side for projecting. So
we have received your these slides. So if there is problem from your side, then we will share those.
Yes, I could not do Google Meet from my laptop, so I'm having to do it from my phone.
Okay, no issues.
Yeah.
No issues.
Okay.
Yeah. So, Dr. Smith, can we start now?
Yes. So I think on behalf of Physical Science Society and the Department of Physics, I would like to welcome Professor Satyaki Bhattacharya, Professor Saha Institute of Nuclear Physics, and all our participants to this evening session of the third day of the ongoing e-STC on advances in high energy physics. Now I would like to request Navdeep to start the proceedings.
Am I audible?
Yes, ma'am.
Good afternoon, all. I would like to extend a warm welcome to Professor Satyaki and all participants for this session. I am highly obliged to say a few words about a speaker of this session. Professor Satyaki has obtained his PhD from Tata Institute of Fundamental Research, Mumbai. He worked at University of California, San Diego between 1999 to 2005. From 2005 to 2010, he worked at University of Delhi and later he joined IISER Kolkatta. In 2011, Professor started working as a faculty member at Saha Institute of Nuclear Physics. He has been a member of CMS experiment at Large Hadron Collider since 1999. He worked for an L3 experiment at Large Electron Positron Collider at CERN during his doctoral research and looked for a signature of supersymmetry for a beyond standard model physics. His current area of investigation includes using photons as a probe to new physics. He has also been involved in searches including looking for a substructure of leptons, quarks, looking for existence of extra dimensions and production of dark matters in high energy for proton-proton collisions. Professor is a renowned name in the area of experimental high energy physics. We are honored to have him with us today. Now I would like to request Professor to take over the proceedings to interact directly with the participants. So
thank you for the kind introduction. I'll wait for the slides. Yes, I can see.
Sir, I think you can start. I am sharing the screen.
Okay. Yeah. Right now I can. Yes. So for some reason, from my PPT file, the slide numbers had disappeared. So yeah, I'll go by the slide number in the PDF box. So. And before I start, one quick question. In the audience, how many are undergraduate students and how many are in masters? Can I get an idea? Is it mostly undergraduate or?
Actually, I think, sir, this is a mix. This is a mix-up of.
Yeah, undergraduate and masters. Okay. Okay, thanks. Okay, so good afternoon, everyone, and let me start. If I go to this slide number 2, just a second, I'll just synchronize my slides also. Okay. So let me start with two pictures. The picture on the left, let's go to slide number 3. The picture on the left, as is marked, is a picture from 1976 talk by Professor Samuel C.C. Tings, who was the spokesperson of the first experiment that I worked on. So this is from his Nobel lecture on the discovery of JPSI in 1974. So the plot on the bottom left corner shows the mass of a pair of electron and positron coming out from the experiment that he and his team were doing at Brookhaven National Laboratory. And what we see here is on the x-axis, the mass of a particle from which presumably the E plus and the E minus, the electron and positron, were coming out. By measuring the momentum and energy of the electron and the positron, they were able to recalculate back the mass, and that is what is plotted in this histogram. So on the y-axis is the number of events, and on the x-axis is the mass of the E plus E minus system. And by November of 1974, they had seen a sharp peak at 3.1 GeV. And that day was the discovery, the experimental proof of the existence of charm quark. That's the second family of quark, a discovery with immense importance in particle physics. This is the same year when the standard model of particle physics got its final form. And the picture on the right is a picture from a 2012 paper published by CMS, the experiment for which I work now. And here also, on the x-axis is the mass of a particle that we were trying to discover. In this case, the particle is the Higgs boson. In earlier talks, probably the standard model has been described and the audience is aware of what is Higgs boson. Higgs boson is a particle that gives mass to all other fundamental particles, according to the modern theory of particle physics. And what we see here is in the CMS detector, CMS is one of the two detectors which discovered this particle in 2012. And this plot was shown for the first time on the 4th of July. And this is from the CMS detector detecting two quanta of light, so two photons. And then CMS measured the energy momentum of these two photons. From the energy momentum, it concluded what is the mass of the particle from which the two photons may be coming. And again, around 125 GeV, compared with the 3.1 GeV of 1974. Now at 125 GeV, we saw a little peak arising out of a falling spectrum, and that is the indication of discovery of a new particle, in this case, the Higgs boson. In the following years, till now, we have confirmed that yes, this is the Higgs boson of the standard model. And this was a momentous time in high energy physics. So between 1974 and the 2012 discovery lies almost the entire history of experimental verification of standard model, which is an exciting, glorious journey. The last piece missing was the Higgs boson, which was discovered at the LHC. And also, between then and now lies the history of calorimeters, which were essential for making these discoveries possible. Next slide, please. Slide 4. So on the left is a zoom of Tings device, again from his Nobel lecture. And he used a 2-arm spectrometer at the alternating gradient synchrotron of Brookhaven National Laboratory to look for electron and positron coming out of a collision on a fixed target. What he needed was to carefully measure the momentum of the electron and positron, and he needed to carefully select a pure sample of electrons to separate it from other particles like protons, pions. And for that, in this figure, there's a little place called marked Z. He used what was then called the lead glass shower counter. Those are the predecessors of what we call calorimeters today. That lead glass shower counter was useful for separating a pure sample of electrons. Many criticized for this expensive spectrometer, and in his Nobel lecture he said that theorists objected that such an expensive spectrometer with such high accuracy is not required. And he remarks in his Nobel lecture that, but however, I have not given much importance to these theoretical arguments anyway, so I knew that I needed a precision device, and I went ahead and built this. And with this, he discovered charm quartz. So another high precision device is the picture on top right. That is the front view of the CMS, the compact muon solenoid detector of LHC. It's 15 meters high, 15 meters diameter, and filled with millions of electronic channels. Let's go to the next slide. So before I get into the topic of today, that is calorimeters, let me quickly describe the process of particle detection in a high energy physics detector. So CMS is a very typical example of a generic particle physics detector of modern day. The two yellow pipes that is visible in this picture coming from two sides, front and back, is the cover for the beam pipe going right inside the detector. And at the center of the detector, proton collides with proton at somewhere between 7 and 13 tera electron volts of energy. The innermost detector layers are a tracking device. Then there are two calorimeter layers, all of which sit inside a powerful magnet. And then outside, the red rings that are visible in this picture, those are the muon detection stations of the CMS detector. Let's go to the next slide for a little more detail. So this is a cross-sectional view of the CMS detector. One octant of the front view, where we can see all the layers of the detector in their frontal cross-section. Now, ideally, we would like to have a detection mechanism so that we can detect all the fundamental particles directly. So what are the fundamental particles? There are 6 quarks, up, down, charm, strange, top and bottom. And then the charged leptons, the electron, muon, and tau, and their corresponding 3 neutrinos, and the W boson, the Z boson, the mediators of the weak interaction, the photon, the mediator of the electromagnetic interaction, and gluon, the mediator of the strong nuclear force, and the Higgs boson, which was just discovered recently. So we would like to detect all of them directly. Unfortunately, only a few of them are stable enough to reach a detection system. Almost all of them either detect or go through a very complex high energy mechanism so that they are not visible. For example, the quarks cannot fly alone. They pull out energy from the vacuum and make other quarks out of the vacuum, and they combine them to form hadrons like protons, ions, and so on. So what are the particles which are visible at a high energy detector? So the list is at the top of this figure. They're muons. You can see the muon in a blue line in this figure. So in this picture, from the left, the concentric rings are the tracking device of CMS. These are concentric cylinders of silicon sensors, and they can track the trajectory of charged particles. So a muon leaves a track there. Then the muon goes through the rest of the detector without depositing much energy, and it reaches the outermost layers of the detector, which are gas-filled detectors and interspersed with big pieces of iron, which are shown in red. So the muon bends. Why does it bend? It bends in a magnetic field. So let me describe a little bit more the setup. So the innermost is the tracking layers. Then the green arc that is being visible just outside the tracking layer is a cylinder made out of crystals, and that is for detecting electrons and photons. This is the electromagnetic calorimeter of the CMS. Following that, the yellow wedges are big brass wedges with scintillator plates inserted in between. Those are designed for stopping and measuring the energy of charged and neutral hadrons like pions, protons, neutrons, and so on. Then the gray shaded ring, that is an arc of a big solenoid, which provides a 3.8 Tesla magnetic field along the beam axis. The beam axis in this picture will be standing out perpendicular to the plane of the slide. And in this field, all charged particles bend. So the muon bends one way inside the solenoid and the other way outside the solenoid, where the field is in the opposite direction. Then with red, one can see the trajectory of an electron in the tracking volume, and then it hits the electromagnetic calorimeter and it deposits its energy there. Then in blue are the charged hadrons like a pion or a proton. So they also leave a track inside the tracking volume because they are charged. And then, it's not in blue, it's, so the green curved line is a charged hadron. And then it deposits energy in the brass volume. Then with a dashed green line, shown is the trajectory of a neutral hadron, like a neutron. So a neutron will not leave any track, but it will deposit all its energy in the brass volume. This brass volume measures the energy of the particles like neutron, proton, pions, which are called hadrons, and is our hadron calorimeter. Then finally, there is in blue dashed line, one can see the trajectory of a photon coming out of the collision center. And it does not leave any track in the tracking volume, but it deposits all of its energy in the electromagnetic calorimeter, and its energy and position is measured. So these are the particles which we are able to measure in any high energy detector. And then there are neutrinos, which are so weakly interacting that they just escape the detector, and that they were produced is found out only by looking at the final state momentum balance. If you see that the momentum of all final state particles are not adding up to zero, that means there is something which ran away with some momentum, and that is called missing momentum or transverse momentum imbalance. That's a signature of neutrino being produced in the detector. So let's go to the next slide. Yes. So now let's get into the topic. Historically, a calorimeter referred to a heat measuring device like the one in the picture built by the first calorimeter ever built by Lavoisier and Laplace. But in high energy physics, calorimeter has a more general meaning. It's an energy measurement device. Let's go to the next slide. Now, in lieu of a customary plan of the talk transparency, I use this borrowed slide from Professor Richard Wigman, who is probably the most. Hello? Hello, am I audible?
Yes, we can hear you.
Okay.
Yes, sir.
Yes. So he's one of the stalwarts of modern calorimetry. And this slide of
Yes, sir, you are audible. Yes, sir.
Yes.
Yes, sir, you are audible.
Yeah,
Continue, sir.
I'm continuing.
Yes, sir, you are audible.
Right, I'm continuing. So this slide summarizes pretty much all that I'm going to talk about. So let me just read out. In particle physics, a calorimeter is a massive detector in which particles to be detected are completely stopped. The absorption process is usually referred to as shower development. The detector is instrumented such as to provide signals that make it possible to determine the particle's 4 vector, meaning its energy and 3 components of momentum. The signals may be provided by a scintillator, by liquid argon, or by water emitting Cherenkov light. The segmentation of the instrumented volume makes it possible to determine the momentum vector of the particles. The signals in the different calorimeter towers indicate the shower axis and thus the direction of incoming particle. The particle type may be derived from the shower profile, the time structure of the signals, and so on. So in the next 1 hour or so, I'm going to describe all the concepts that are summarized in this slide. Moving to the next slide. So what does a calorimeter measure really? If it doesn't measure temperature, what does it measure really? Although the calorimeter's energy, even in a high energy calorimeter, when a particle hits the calorimeter, ultimately it heats up the calorimeter. Mostly the energy becomes heat, but that leads to a minuscule rise of temperature, and we are not interested in that. So high energy particles entering the calorimeter will interact with the nuclei, the electrons, or the atoms as a whole, and will lose energy. The secondary particles produced interact further to produce some detectable signal like light or charge. Then there has to be some electronics connected with the calorimeter unit, which will collect the light or the charge and then convert it into a voltage or current pulse. The principle of calorimetry, the core principle of calorimetry, is that the pulse height is proportional to the emitted signal, light or charge. And then that signal is in turn proportional to the energy of the incident particle. So if we can measure the pulse height accurately, we can measure the energy of the particle accurately. On the right, I have shown one example. And if we look at the bottom picture, this is a transparent crystal, a compound of lead tungsten. It's a heavy crystal, and it's a scintillating material. It's 23 centimeters long and 2.2 centimeters by 2.2 centimeters inner face. At one end, one can see little photosensor connected to this, and this is essentially what is a calorimeter. This is the unit of electromagnetic calorimeter of the CMS detector. Let's go to the next slide. Now, in high energy detectors, out of these basic units, we build huge detector systems. On the left, on the right, you can see the picture of the assembled electromagnetic calorimeter of the CMS. It's a cylinder containing 75,000 of those crystals which you just saw, each one with their associated sensors and electronics. It's a homogeneous calorimeter, meaning it's one piece of material which absorbs the energy of the particle and also produces the signal, and you need one sensor at the end of it to get the signal out. It operates inside 3.8 Tesla magnetic field that runs along the axis of the cylinder, if you wish. And the readout is by avalanche photodiodes or vacuum photodiodes. The electron and photons are completely stopped by this device, and their energy is measured at high precision. Let's go to the next slide. Now, what are the steps of the energy measurement? The first step is, so we, once the pulse comes out, the analog pulse is then digitized by sampling the analog pulse with time. And then we get the pulse height in units of analog to digital converter count, so ADC, and then that is to be converted ultimately into some units of energy, typically GV, giga electron volts, and that conversion needs determining the conversion constants, and that is called calibration. Then one has to remember that when a particle like an electron or a photon hits the calorimeter, it does not deposit energy just in one crystal or one cell. The energy spreads in nearby cells. So one will have to find the clusters of energy deposit, which is an extremely important step in calorimetry. It's a pattern recognition process, forming the clusters. And then finally, from the cluster, one reconstructs the energy, position, and time of hit of the incident particle, in this case, an electron or a photon. So the performance of such a system is measured by how accurately we can measure the energy, position, and time of hit. This is, or in technical words, energy, position, and timing resolution. Remember that at the core of this is the assumption of linearity, that is assuming that the signal produced is proportional to the energy. Now, this may not be true when you are measuring energy starting from few tens of mega electron volt all the way up to a tera electron volt or so. So linearity is another important performance feature of a calorimeter. Let's move to the next slide. Now, this is a wonderful picture showing what we would have seen if we could get inside the calorimeter volume. This picture is from an old bubble chamber picture, but essentially the same thing will happen in the CMS calorimeter crystals or in any piece of material with which we make a calorimeter. So it shows a 50 GeV electron coming inside the bubble chamber from the left. And then after entering, soon it will give out a Bremstral photon. That Bremstral photon will pair produce and go into an E plus E minus. That electron and positron will give out more Bremstral photons, and they will again pair produce. So we will get a cascade reaction, and that is called a shower. We see the charged particles, the electrons and positrons, bending away, curling away in a magnetic field. And if we look at the red circled region, this is one example. We see two curved lines coming out of nothing. So that point is a point where a photon converted into an E plus E minus pair, and the E plus E minus pair bent away in two different directions. So this is called an electromagnetic shower. That's the first thing that happens inside an electromagnetic calorimeter. Instead of a photon, instead of an electron, had it been a photon, the first reaction would have been different. The photon would have gone in, and soon it would have converted into an E plus E minus pair, but then the same electromagnetic shower would have formed. So, please skip this one. This is a repeat slide. Okay, so let's go to slide number 14. Yes, so let's take a closer look at this process. What is happening at the most fundamental level? So that is given by this Feynman graph on the right corner of this slide. So note the points 1, 2, and 3, where something is getting emitted or absorbed. That's called a vertex. So the two incoming players are an incident electron coming from the top and a nucleus of some atom inside the material, which is coming into the play. And then the electron, so to speak, absorbs a photon that is coming out of the electric field of the nucleus. So the nucleus has charge. Z is the number of protons, and Ze is the charge of the nucleus. That charge will have electric field, will create electric field around it, and electric field means nothing but photons. So the electron absorbs a photon, gets scattered off at point 2, but in the process at point 1, it emits a photon, and that process is called Bremstral. Now we know from the theory of fundamental particle physics that the the quantum mechanical probability amplitude of a photon getting emitted at point 3 is proportional to Z square root of alpha, where alpha is the fine structure constant, E squared by 4 pi, E is the charge of the electron. Similarly, the probability amplitude of a photon getting emitted at point 1 is proportional to square root of alpha, and the electron absorbing the photon is another square root of alpha. So and then to find out the probability of this whole thing happening, we need to square up the probability amplitude. That's the rule of quantum mechanics. When we do that, we get the rate or the cross section of this process, and it is proportional to Z squared, the atomic number of the absorbing material, alpha cube, that is 6th power of the charge of an electron, and it's inversely proportional to the mass square of the electron, which comes from the fact that electron transfers some momentum to the outgoing photon. Now, this process is known as Bremstral in presence of a nucleus, and this is the important process for shower formation. The atomic electrons also have their electric field. Bremstral can happen in their presence, but the rate of that process is proportional only to the first power of Z, and for heavy materials, this is not so important. Going to the next slide, then so the electron will, let's look at this formula which says dE dx. So dE dx means the rate of energy loss by the electron while it's traveling unit length. So the rate of energy loss will be an exponentially falling function. The electron will lose energy exponentially. And the constant of that exponential is called radiation length. It's defined as the mean length in a material within which a high energy electron loses all but 1/eth of its energy by Bremstral. So typically in a high Z material like lead or copper, the radiation length is 1 centimeter compared to 30,000 centimeters in dry air. Let me skip the details. There are a lot of details in these slides, technical details, which I will not be able to say in words, but those are there for future references and if there are questions. So how long, let's go to the next slide. Now, how long will the electron keep radiating? It will keep radiating till it reaches critical energy. What is critical energy? Critical energy is that energy of electron at which the energy loss by radiation of photons becomes equal to the energy loss by ionization. Electron is a charged particle, so it will ionize also. And the critical energy is inversely proportional, roughly inversely proportional to the Z of the material given by this formula in the blue box. On the left, we see that, so the x-axis is the energy of an electron, incoming electron in MeV, and the y-axis is the fractional energy loss per unit length by the electron. If we look at the brown falling line, that is the line of electrons ionization. And there are other processes for low energy electrons below 10 MeV, like elastic molar scattering or E plus E minus going to E plus E minus, which was calculated first by Homi Jahangir Bhabha and is known as Bhabha scattering. And so we see that at low energies, ionization is the dominant process of energy loss. But then the purple line showing the loss due to Bremstral, that takes off from around few tens of MeVs and becomes the dominant process. The point at which these two lines cross is the critical energy point. So it's defined not only for electrons, but all charged particles. So now let's move to the next slide. What about the photons? It's pretty much the same story at the fundamental level. Again, a very similar Feynman diagram. From the top corner of the diagram, there is an incoming photon now instead of an incoming electron. That's the only change. And that photon now absorbs another photon or interacts with another photon from the electric field of the nucleus. And then they annihilate and produces an E plus and an E minus in the final state, which are on the right side of this diagram. The same fundamental physics, same 1/m square dependence, and then they're proportional to Z square and alpha cube. So the photon will come inside the crystal that I showed, and soon after crossing within one radiation length, so within less than a centimeter, it will get destroyed through this reaction of producing E plus E minus, and then the E plus E minus will do Bremstral, and this goes on. So let's look at the rate of the pair production and when it becomes important. So the pair production cross section is proportional to z square alpha square by me square, which we just discussed. It's shown on the right panel. If we move to the next slide. Yes. So on the let's not look too much in the details of the formula. The graph on the right says it all. Below 10 to the power 0 MeV on the x-axis is the energy of an incoming photon, and below 1 MeV, processes like Compton scattering and photoelectric absorption, shown in green and red respectively, are important. On the y-axis of this plot is attenuation in grams square, centimeter square gram. So essentially, it is energy loss per unit length multiplied with the density. So that's what gives the centimeter square gram inverse. Just consider it as rate of reaction. The black line shows the total rate of reaction. It keeps falling up to about 10 MeV. Then if one looks at the blue line, one sees that starting from 1.02 MeV, that is twice the electron mass, the pair production takes off. And by the time we reach 10 square MeV, that is a GeV, pair production is essentially all that a photon does. So for high energy detectors, the pair production is the single most important process in calorimetry. The total rate of pair production, the sigma pair production, is 7/9 times the atomic number A of the material of calorimeter divided by the radiation length of the calorimeter times Avogadro number. So the 7/9 is an important number, and this means that a photon will have a mean free path which is 9/7 times the radiation length. So radiation length tells us what length of a detector will absorb what energy electron or photon. So if we go to the next slide, slide 19. So here is this slide shows a very simplistic model of shower formation inside a calorimeter, yet it's useful. In pink is shown the radiation length. So in this simple model, a gamma or a photon comes from the left, and within one radiation length, it produces an E plus and E minus pair. And then every radiation length, either an E plus or E minus emits a photon, or a photon produces E plus E minus, and that's how the shower propagates. So if one assumes that this one reaction happens every radiation length, and a photon gives 50% energy to E plus E minus, then one can build a shower model. In the bottom panel in blue, it is the top formula dE/dt shows the energy of shower per unit length derived from this model, and that is again an exponential fall multiplied with a power law. So it's depth to the power alpha e to the power beta t, and then if one plots this as a function of depth of the material, so the x-axis can be thought of as the depth of the crystal going from left to right in centimeters, and on the y-axis is the energy deposited by the shower per unit length. Green is for 1 GeV photons or electrons, and the red is for 1 TeV photons and electrons. So the maximum energy deposit, the peak of these curves, move towards the right with the energy. This peak is called the shower maximum, and it's given by 1.4 times log of the incident energy of the particle E0 divided by the critical energy. And the total number of shower particles after some depth T is E0, the energy of the incident photon or electron divided by the critical energy. So in this, we can see that going up to 30 or 40 centimeters of material, the shower gets completely absorbed. Typically, the shower maximum happens within 10 radiation lengths. 23 centimeters of lead tungsten crystal, which is the crystal of CMS electromagnetic calorimeter, completely absorbs, it provides 26 radiation length, and for hundreds of GeV electrons and photons, they completely absorb the energy. Now, how wide is the shower? We got an idea of how deep the shower develops. How wide is the shower? Let's move to the next slide. And the Bremstral and pair production are the main processes of shower formation. Both are extremely forward peaked. They're almost parallel to the direction of the incoming particle. So the core of the shower is very narrow. However, as the shower develops, we have more and more particles, and the original energy gets shared. And once the energy per particle reaches close to the critical energy, then atomic scattering processes become important, and that's how the shower spreads. Moliere radius is a concept related with the spread of the shower. We can look at the bottom right picture on. Let me first define Moliere radius. So if you imagine a cylinder whose axis is along the direction of the incoming photon or electron, then a cylinder of radius equal to Moliere radius will contain 90% of the shower energy. For lead tungsten, it's about 2 centimeters, it's 2.2 centimeters. And the Moliere radius also is proportional to A by Z, atomic number mass number by atomic number. The plot on the right bottom panel shows the lateral profile of the shower. It essentially shows that most of the energy is contained within 1 Moliere radius. The x-axis in this plot is the lateral spread of the shower expressed in the units of Moliere radius. And as one can see, most of the energy is contained within 1 Moliere radius. So that's already a lot of technical details. Now, let me stop at this point quickly. A lot of information I have already given. If there are any quick questions, I can take it now. If there is any quick clarification, otherwise I'll go ahead.
The question will be taken at the end.
Questions at the end? Okay. Okay. All right. So now let's move to the next step that I mentioned. So we understood well what an electron or a positron or a photon does.
Sorry, Professor Satyaki, for a minute.
Yes.
I think let's better ask the questions which have been collected till now, right? So that participants can understand the incoming parts as well, right?
Yeah, if there are quick questions, because this is a 1.5 hours talk and there's a lot of information. So it's better to clear the doubts, otherwise one will be lost.
Okay, there is a recent question. He asked, please elaborate a bit more about how the calorimeter measures the energy of weakly and rarely interacting particle. Why, as usually, escape the detector?
Okay, yeah, right. So the calorimeter doesn't measure the energy of weakly or rarely interacting particle. At the very end of my talk, I will just touch upon this. I'd just like to mention that this question is of immense importance because at the Large Hadron Collider, most of the new physics discovery relies on weakly interacting particles which leave no signature in the detector. I'll comment more at the end. Any other quick questions?
There is a question. How and what is the main difference would occur if instead of photon there is a scalar Higgs? Actually, his question is up. Let me see.
So maybe if the participants can directly
Yes,
want to ask this
Ruchi,
question, then go ahead.
Yes, sir. Ruchi, please, can you ask your question directly? What was your question? Ruchi, are you there?
Hello?
Hello, yes,
Yes.
we can hear you.
Can you hear? Yeah. Okay. I was asking that till now, Satyaki sir is discussing about how a photon would decay into electron pairs and how it will be measured, the data analysis, everything. But I'm just asking, what will be the major difference if instead of the photon, which is a spin 1 boson, spin 0 boson, the scalar would be there, then what will be the major difference in all these plots?
Okay, so very quickly, the Higgs boson, which is a spin 0, the Higgs boson
That's an
has...
example, like Higgs is the only scalar particle in our theory until now, but instead of that, even if some other resonance particle, which is a scalar, is there, then
Yes, so Higgs is the only spin 0 fundamental particle that doesn't reach the detector. So it doesn't matter so much whether the particle is spin 0. It does, but whether the particle is spin 0 or spin 1. What matters is what type of interactions it is able to do inside a piece of material. So photon can do, so what I have, one line summary is of what I have told so far is that if a high energy photon or an electron hits a piece of material, what kind of reactions it will do. And what we have seen is that they will do mainly electromagnetic interactions because they have charge. So if that spin 0 particle is it does not have charge, it will not do these interactions. If it's a charged particle, then it will ionize. If it's a strongly interacting particle, then it will do hadronic interactions and so on. So it's the interaction that matters rather than spin.
okay, and that's how Higgs, like scalar, has more dominant other interactions like top pair or heavier particles.
Very quickly, the Higgs doesn't even get to see the detector. The proton-proton collides, the Higgs gets produced inside the beam pipe and it decays immediately. So it doesn't reach the detector. The TT bar production, or so the Higgs that we have discovered is 125 GeV Higgs. the top mass is more than that, so it doesn't really easily produce TT bar. But BB bar, for example, if it produces right at the collision point practically, and it's the decay products of the BB bar or the jets of hadrons formed by the BB bar. That is what goes in the detector, and that's what we see. We do not ever directly see the Higgs going in the detector.
Yes, sir. Okay, thank you.
Okay, so let's move on. Right. So the next step is, so we see that a shower is formed inside the calorimetric material, and then that shower absorbs all of the energy. What happens to that energy? Let's move to slide 21. I'm not able to see the slide anymore.
Actually, we can see it, friend.
You can see it at your, oh, okay. Maybe because I've been, sorry. Okay. So the next step is from the shower to signal. For a scintillating crystals, it's light. For other devices, it could be charged. So very quickly, in case of a scintillator, the end particles of the shower, they will interact with the lattice if it is an inorganic scintillator, or with the molecules in case of a plastic scintillator, and then electrons can get excited from valence band to conduction band. And in presence of impurities, there are intermediate levels. So that's why presence of impurities is important for these scintillating devices. There are intermediate levels, so a two-step transition will take place. And in the intermediate step of transition, which is called quenching, so a photon can come out to which the material itself is transparent, meaning the photon will get out of the material. So such materials which have this property are scintillators. Pictures of some are there in the bottom panel. They come in various size and shapes. Zinc sulfide is an inorganic scintillator which Rutherford used for his famous experiment. Bismuth germanate is a crystal which was used for one of the detectors, L3, in which I had done work for my PhD. The calorimeter crystal was bismuth germanate. Incidentally, this was the experiment which was led by Samuel C.C. Ting in later days of his career. Then liquid argon also produces scintillation that is used in ATLAS, the other proton-proton collider detector at LHC, and plastic scintillators are also used in CMS hadron calorimeter. The light, the photon, scintillation photon output can widely vary from tens of thousands to just a few hundred photons. And then the number of photons is a random number. From collision to collision, it will vary. The number of photons is Poisson distributed, which means that its fluctuation goes as square root of n. And since the number of scintillation photons produced is proportional to the incident energy, then that means that the uncertainty in the energy measurement will go as square root of the energy. So if 100 GeV electron falls on a calorimeter face, the uncertainty will be of uncertainty in its measurement will be square root of 100 or proportional to square root of 100. We will see the details of that. The light collection, when light is the signal, there are various mechanisms. One can have a directly coupled photosensor, like I showed in the lead tungsten crystal picture, or the light collection can happen through optical fibers. Then the next step is, once the light is collected, what do you do with that? That is then converted into an electrical pulse. That electrical pulse is shaped, for example, continuing with our CMS electromagnetic calorimeter example, we have a MGPA, a multi-gain preamplifier with a very wide dynamic range because it has to shape pulses from pulses coming from few tens of MeV photons and electrons all the way to tera-electron volt electrons and photons. So this MGPA shapes the electrical pulse coming out of the photosensor. Then at Large Hadron Collider, a collision happens every 25 nanoseconds, and the LHC clock ticks one tick every 25 nanoseconds. We have a 12-bit ADC, analog to digital converter, which converts this analog pulse into digital samples. And what we can see in the top right picture, on the x-axis is the time, and on the y-axis is the pulse height. The red dots are the times at which the pulse was sampled. One sample is taken every 25 nanoseconds, synchronous with the LHC clock. Then 10 such time samples are used to fit a shape, which is shown in the bottom picture. A functional form is fitted through the time samples, and the output of that fit is the pulse amplitude. So from the fitted function, we get the pulse amplitude in units of ADC. So in the bottom plot, one shows on the x-axis is the LHC clock ticks. So 1 unit here is 25 nanoseconds. And on the y-axis is the fitted pulse amplitude. And then the second dotted line on the left shows where the pulse maximum happens. That is denoted by amplitude max, A max. And the time of this happening is denoted as T max. So these are two quantities, amplitude and pulse, which are measured for every crystal. And that is what is stored in the recorded data. So this A max contains the information of energy of the particle. This is in units of ADC. Now this has to be converted into GeV. That process belongs to calibration. Calibration is much more than that. Let's spend a couple of minutes on this. So calibration is an extremely critical step for performance of any calorimeter, and is to be done by great care. Our group has been involved in the calibration of hadron calorimeter of the CMS for many years. And so with calibration, the ADC counts will be converted to GeV. And this can be done with known energy beams in beam test. Now, every calorimeter cell, that is every crystal, is different from the other. Their response, that is the light output for different energies, for the same energy, is different. So this difference in response needs to be taken care of. So every crystal's GeV unit energy has to be multiplied by a small constant close to 1, that is called intercalibration constant. Then the crystals decay with time. As the crystals age, they form color centers, they become opaque, so their light output reduces. That needs to be taken care of. Those are correction factors derived by laser. Then finally, once the experiment starts, while the experiment is going on, one has to do ongoing calibrations with particles of known mass. Those are called standard candles. So, and then some energy measurements requires measuring in a part of the energy in electromagnetic calorimeter and part of the energy in the hadron calorimeter. Then one needs to combine the ECal and HCal deposits with appropriate constants. Those are also part of calibration. And extreme care is needed for that. It is difficult to do calibrations for longitudinally segmented calorimeters. And Monte Carlo studies may be important for this. So now the next step, once you have the ADC to GeV converted and corrected energies from each crystal or calorimeter cell, then the next step is known as clustering. That is, a typical electron or a photon will deposit energy in many cells, and you need to group those cells. Here, we see a segment of the calorimeter in a sketch in the next picture.
Professor Satyaki, maybe, so should we move to the next slide?
Yes, next slide.
Yeah, okay, thank you.
Yes, so here in this, we see each box in this sketch represents one crystal of the electromagnetic calorimeter, and the crystals in red are the ones which had energy deposit. Then one needs a detailed algorithm for clustering these crystals together, which will tell us that all this energy deposit is coming from one photon or one electron. So we need to sum up the energies to get the energy of the photon or the electron. That is called clustering. It is done now with something called multi-Gaussian fit. Earlier, there was another algorithm. The bottom line is that the clustering algorithms are very important and is a very interesting pattern recognition exercise. In future, we will probably use neural networks for such tasks. So, which is already being done. Deep networks are being used. I won't have time to talk about that. Let's move to the next slide. And now, in this slide, we see the final result of all of this exercise. So, pi zero, neutral pion, is a particle whose mass is extremely well known, and a lot of pi zeros are produced in E plus E minus in hadron-hadron collision at LHC. So one of the very first thing that CMS did was, and pi zeros decay to 2 photons. So the electromagnetic calorimeter detected these photons, clustered their energy, measured their calibrated energy, and they adjusted the calibration constants such that it gives the pi zero mass back. So on the left, you see the result of a simulation. The peak in red is the mass peak of pi zero. The x-axis is mass in GeV, and the red dashed line shows that the measured mass of pi zero is coming out to be 136.9 MeV, which is within less than 1% of the best known mass of pi zero. And this is from simulation. And on the right-hand side, you see the same exercise done from real data using just few hours of first LHC data taken at 7 TeV of center of mass energy. This is a big success picture of the CMS's electromagnetic calorimeter. It shows how well our detector simulation describes the reality, and it shows how accurately we can measure the energies of electrons and photons with our calibration procedure. So now, in the interest of time, so I have about how much time left? 25 minutes.
So as such, actually, there is no time limit. So I think you can pace the way you want.
Okay, but beyond 1.5 hours becomes difficult for students.
Yes,
also.
I understand that.
Yes. So I'll maybe pace up a little bit, and let me.
Actually, there is a sort of some trouble as well on our end. Actually, we lost power. So Dr. Arvind was changing slides for you. So he lost his internet connection. Please allow us a minute actually to just shift the internet connection to our mobile devices. Okay. So in the meantime, actually, there was a question.
Hanji sir, can I ask some questions?
Sure. Please go ahead.
Yes.
Okay, so thank you, sir. Sir, there's a question. Are radiation length and skin depth related to each other?
Well, skin depth has to. The short answer is no. So skin depth has to do with much lower energy processes, and radiation length essentially measures how deep a photon can penetrate inside a piece of material when the energy of the photon is in is GeV or more.
Okay, sir. Here is another question. How do we dispose the excess energy of high energy particles after each experiments?
How do we
dispose the excess energy of high energy particles after each experiment? Question was asked by Maria.
Right. Okay. So that, in a way, I have already answered. So as you saw, that all the electrons and photons that got radiated, all the high energy radiation, they got absorbed in a 23 centimeter long thick crystal. So then the entire energy from the radiation eventually got converted into heat and light, actually very little light and mostly heat. And also we will see in a minute that they also get absorbed by doing nuclear interactions like fission, breaking up nuclei, and so on. So that is what happens to the energy of the radiation. They just get absorbed by the detectors. So that's why we say that the detectors burn with time.
Okay, sir.
Okay.
Now I would like to request some participant to ask questions.
So maybe Navdeep,
Okay,
I think
sir.
we can repeat that exercise at the end. So we are good to go
Okay.
actually from our
Okay,
side
so
as
we're
well.
ready? Okay, sir.
Yep, we are.
Okay.
Thank you, sir.
Okay, so in interest of time, let me skip the next two slides. I can come back if there is a question. These are somewhat technical. Slide 20. Hold on. Yes, slide 26 and slide 27. The bottom line is that when we have energy estimation from two different calorimeters combined, like electromagnetic calorimeter and hadron calorimeter, then there are many pitfalls. And with the energy, the linearity of signal may be lost. So the calibration constants may not be constant anymore. They may become energy dependent. There's a whole chapter on this issue in Wigman's seminal book on calorimetry. Let's go to slide 28. Yes, here also I will skip the details of the steps and give a summary of the main point. So I already mentioned that the energy resolution depends on the fluctuation in the number of photons produced inside the scintillating crystal. Now, going back one step, that number of scintillating photons in turn depends on the total track length of all the electrons and positrons produced in the shower. And in fact, not the total track length, the fraction of the total track length that are produced by electrons and positrons above a certain threshold. If we combine all of that, the bottom line is given in the blue box in the end. And so what we see, sigma E by E is the relative uncertainty in energy measurement. Sigma E is the standard deviation in the measurement of energy, and E is the energy of the incoming particle. So we see that sigma E by E, which is called relative resolution, is proportional to square root of Z by A, where Z is the atomic number and A is the mass number of the absorbing material. And it is proportional to 1 over square root of Fs, where Fs is the fraction of charged particles in the shower that will give a detectable signal. So the bottom line is one can try to design calorimeters which maximizes Z by A, minimizes Z by A and maximizes the detectable track length. Thus, you can minimize sigma E by E or make your calorimeter more accurate. But there is no escape from this intrinsic resolution. You cannot do better than that. Next slide. The full the full resolution, of course, depends on other things like electronic noise and shower leakage. Those are parameterized with other constants. Here it is given as A, B, and C. A is the constant showing the intrinsic resolution, and since the sigma E goes as square root of E, then sigma E divided by E falls off as 1 over square root of E. And then to get the total resolution, you have to take the square of all these individual components and then take a square root, that is known as sum in quadrature. That gives the total resolution. So now let's see an example. So CMS, next slide, please. CMS achieves an energy resolution, A term 2.8%, B term 12%, and C term 0.3%. And the sigma E by E plotted as a function of E is there in the left plot. At high energies beyond 100 GeV, one can see what matters is the last term, the 0.3%. Other terms die away. We can look at the red line, that is the total energy resolution as a function of the energy of the incoming particle. And the total energy resolution improves with energy, and the best that we get is 0.3%. So you can calculate. It's for a 100 GeV electron, then 0.3% would mean 300 MeV. Actually, we do better than that. And on the left bottom plot, I have shown the energy measurement accuracy for the precision for electrons as a function of its angle with respect to the beam axis. Let's move to slide number 29. Now, so far, we have been talking about calorimeter, which is just one piece of material which absorbs the energy and measures the energy. Most calorimeters are not like that. They have absorbing material and energy measuring layers. These are known as sampling calorimeter. The basic idea one can see in the top left picture of slide 31. So we can go to slide 31. The top left picture shows an old cloud chamber picture of an electron shower. So one can see that the vertical bars are lead absorbers, and in between those are cloud chambers. So the shower is being detected in the cloud chambers, but most of the energy loss is happening inside the lead. So the lead is the absorber, but it does not detect the signal, and the cloud chamber, which does not absorb much energy, is detecting the signal. Such a device is a sampling device. That was an old device, and I take the example of Atlas liquid argon calorimeter as a state-of-the-art modern device. The top right picture shows the whole Atlas liquid argon calorimeter. The bottom left, it has a very interesting structure. The bottom right shows the structure. It's made out of zigzag structures, which looks like an accordion. So the bottom left picture shows a schematic of the accordion structure, and many such accordions are put together. If we zoom inside the accordion, we will see that the blue regions are liquid argon filled gaps. Then the red lines are the readout electrodes, and the gray lines are lead absorbers. In this case, they're at an angle with the incident particle. But this is an example of a sampling device. Here, this is also an example of a liquid being used for a calorimeter. Okay, so let's move to the next slide very quickly. With this, Atlas achieves a 0.17% of energy resolution at high energies. I'm left with 10 minutes for a lot of stuff. So let me skip through. If there are questions, then I can come back. It's more like material for 2 lectures. So, but let me very briefly mention so we understood what an electron and a photon does inside a calorimeter. Let's ask next what a muon will do passing through a calorimeter. Remember that muon is charged, so it will also do Bremstral. But remember that in the Bremstral formula, there is a 1/m square. The mass of the muon is 200 times more than electron, which means that its Bremstral probability is 40,000 times less. So for muons or heavier particles, Bremstral is not the way of energy loss. It will lose energy by ionization. These three gentlemen, 3 great physicists, Hans Bethe, Felix Bloch, and Enrico Fermi, had found out the theoretical formula for energy loss of particles like muon in a piece of material. It's known as Bethe-Bloch formula with Fermi's correction. And the formula essentially says that the amount of ionization is proportional to the square of the charge of the incoming particle and inversely proportional to the velocity square of the particles. And so one can see a track of a iron ion and track of a thorium ion in and the amount of ionization that they produce in the picture on the right. Let's skip the details of the formula, which is on the next slide, and go to the slide which is next to next. And it shows, so this curve, the famous Bethe-Bloch curve, shows the energy deposit per unit length on the y-axis as a function of momentum of the particle in the x-axis. So it shows the region that I pointed with a red arrow shows that so the x-axis is essentially momentum. Beta gamma is the relativistic velocity of the particle, and gamma is 1 over 1 minus beta square. But remember that momentum is mv, where m is the moving mass of a particle. So that is m naught gamma. So m naught beta gamma is essentially the momentum of a particle. So beta gamma is essentially the momentum of a particle divided by its rest mass. So take the x-axis as momentum of the particle. So we see that as the momentum of the incoming particle increases, its ability to ionize decreases. And there comes a point when its ability to ionize, shown with a red box in the curve, is minimum, and particles beyond that energy is called a minimum ionizing particle. It happens at around beta gamma 4. So a muon with about 400 MeV of energy or more will just pass through the electromagnetic calorimeter of CMS and hadron calorimeter of CMS as a minimum ionizing particle, depositing few hundred MeV of energy. Now, moving to the next slide, now comes the most difficult part of calorimetry, that is hadrons interaction inside a calorimeter. So if we think of, now let's ask, what will a charged pion do if it is allowed to pass through the lead tungsten crystal of CMS that you saw? So what will happen, and we have seen this in simulation as well as in the real experiment, that most of the time it will just pass through like a muon. It will do a little bit of ionization and not much. But some of the times, and actually not that small fraction of the time, actually I think it's more than 50% of the time, it will do a nuclear interaction. And what are those interactions like? We can see it from this old emulsion plate picture, in which from the right, one can see with the red arrow, a 30 GeV proton is coming in and then at the dark center, it is doing a hadron interaction. And then one can see a whole bunch of charged tracks coming out of the hadron interaction. So the tracks which have not many points in the nuclear emulsion, those are shown with blue arrow. Those are pions and fast spallation protons. But then the thick lines shown in red are sorry. Something happened to my, something happened to my screen, actually. So the thick lines shown in red are coming from protons which are slow moving protons, and they ionize a lot. So we'll remember that a hadron will do such interactions inside a piece of material, and the protons that they produce, the non-relativistic protons that they produce, are the main source of energy deposit. So we can move to the next slide. And yes, so this shows, so just a second, we'll synchronize mine. Yes, so on the left, this shows the picture of a typical hadron shower in a piece of sampling calorimeter. The red is pi zeros produced in the shower, and the pi zeros then convert to a pair of photons. They always become a photon pair, and then the photons start their electromagnetic showering, which you can see in red. And the core of the shower of an incoming hadron is actually an electromagnetic shower. But then the blue lines are coming from charged pions, protons, and those are responsible for the shower spreading in the lateral dimension. These showers do not have a specific nice shape like the electromagnetic shower. From event to event, they vary a lot, which is shown in the right 4 panels. These are energy deposit of a 270 GeV pion, 4 different events, 270 GeV pions coming in. And on the x-axis is the depth of the calorimeter, and on the y-axis is the energy deposited per unit depth. And one can see that the first pion's energy deposit pattern is very different from the seconds from third and fourth. So there is very wide fluctuation in energy deposit pattern, which means that the hadron energy measurement will have larger inaccuracy. Then in the next slide, I have shown the typical energy deposit of a hadron as a function of depth of the calorimetric material, and on the right, the lateral spread of the shower. I won't take time to describe the technical details, but what we can, but let me just mention that just like radiation length for hadrons, which deposit energy by doing nuclear interactions, a quantity called nuclear interaction length is defined. Actually, it was written in the previous slide. So this is the average length within which a nuclear interacting particle will do a nuclear interaction. And for high density material, it's typically 1 or 2, within 1 to 2 meters. And what this plot, the left plot, is telling us is that within 10 nuclear interaction lengths, so that is 10 to 20 meters of heavy material, a hadron, a high energy hadron like a proton or a charged pion, will deposit all of its energy. I can come back to the details if there is question. Now, moving to the next slide. There is, just like electromagnetic shower, there is shower model for hadrons, but it's much more difficult to model the shower. But in the top right picture, we can see what happens to a hadron. So if a neutron comes in, it travels one nuclear interaction length marked by lambda in the pink box. So then it does some nuclear interaction and produces some pi zeros, charged pions, protons, neutrons. Now the pi zeros will convert to photon pairs, and that will produce electromagnetic shower that is known as the EM component of a hadronic shower. The other particles will form what is known as non-EM component. Now, the second tricky part of hadron energy measurement is that the signal produced by the EM component, that is, let's say the number of scintillation photons produced per MeV of energy deposited, is much more for the EM component compared to non-EM component. So this is known by the E/H ratio. E is the response of the electromagnetic component, and H is the ratio, or H is the response by the hadronic component, and they are very different. The reason why they are different can be seen from the fraction of energy deposited by various non-EM components. So we see that 40% of the energy in the non-hadronic component is invisible, meaning this is energy that goes in overcoming the binding potential of the nuclei and breaking them up. They do not produce any visible signal. And so 40% goes in that. And so the signal produced by this component is a lot less. So typically, the E/H ratio is much greater than 1 for hadron calorimeter, which is shown in the next slide. And that is a problem. One question that research in hadron calorimetry has tried to answer is to how to make this E/H ratio to 1. And that is known, so the calorimeters which can make this ratio 1 are called compensating calorimeters. Let's go to the next slide. Yes, so the next slide shows the problem in a little bit more detail. The left side plot shows that the average fraction of energy that goes in the electromagnetic component of the shower, and bigger that fraction, better is our energy measurement. That fraction, the FEM, changes with the energy of the incoming particle. So a pion from 10 GeV to 200 GeV will have EM fraction changing from 0.3 to 0.6, something like that. And also, for a given energy pion, like for a 150 GeV pion, we see on the right plot that the EM fraction is not the same for every event. From event to event, it has a big fluctuation. So all of this worsens the energy measurement of a non-compensating calorimeter. We can go to the next slide. And people have tried different ways of making compensating calorimeter. W. Willis et al., they used uranium, thinking that energy released by fission will compensate for the missing binding energy, and they made uranium calorimeter. But eventually it was found that the E/H ratio depends on the Z of the absorber, the amount of proton, the amount of hydrogenous material that is used in the sensitive part of the detector, and the amount of protons in the signal. So these are a lot of details. Let's move on to the next slide. This is an interesting plot. So this shows, so UA1 and UA2 were experiments in the 80s which were responsible for discovery of W and Z boson. So this plot is from UA2 calorimeter, looking at hadronic decays of the Z boson and the W boson. and shows the performance of a non-compensating calorimeter. On the right plot, one can see that they fitted. So they looked at events where they looked at events with 2 sprays of hadronic particles, and from that they tried to measure the mass of W boson and Z boson by fitting 2 Gaussians shown with a red dashed line and blue dashed line here, and they found that the W mass is around 80 GeV and Z mass is around 90 GeV. But then the Gaussians were very wide, which meant that their accuracy of mass measurement was not all that great. So since then, hadron calorimetry has come a long way. If we go to the next slide, this is modern day hadron calorimeter, CMS. This is also a sampling calorimeter, and it's a non-compensating calorimeter with E/H 1.4. The bottom, let's start from the bottom left picture. Our calorimeter hadron calorimeter is made up of brass, which were obtained from Second World War used artillery shells. You see 4 workers sitting on Second World War's artillery shells. Those were given a shape, the bottom row middle plot, into wedges of brass, and those wedges are the building units of our hadron calorimeter. Those wedges are put next to each other to make rings, and inside those rings there are little slits. Inside those slits, scintillator plates like the one in the bottom right are inserted, and inside those scintillator, the little wire that we are seeing, those are optical fibers. They run through the scintillators and then they go to photosensors, hybrid photodiodes. That is our hadron calorimeter. All of this is put together and makes the CMS hadron calorimeter, which is the top right picture. This is the CMS calorimeter being lifted by a crane and going inside the magnetic solenoid coil. And let's move to the next slide. I'll just mention that now with improved calibration techniques, and we are involved in this, we achieve a 2% accuracy in calibration. This is a technical point. Single charge pions are used for calibration. The plot shows on the x-axis the momentum of a charged particle, and on the y-axis the calibrated energy. A 45-degree line would indicate perfect calibration. So we achieve that within 2%. So the next slide shows the hadron calorimeter resolution. The stochastic term, which is something like 2% for the electromagnetic calorimeter, is 100%, 120% for the hadron calorimeter. We can move to the next slide. So we see that the resolution of a hadron calorimeter, especially a non-compensating one, is not all that great. People like Wigman have tried for years to improve this, and DREAM is a detector concept, which stands for Dual Readout Method Detector. Tries to improve on that, and they claim that they can make a hadron calorimeter as good as or maybe close to an electromagnetic homogeneous electromagnetic calorimeter. I won't go in the details of that. The top right picture shows the DREAM detector, which is essentially filled with optical fibers, 200 centimeters lead through which optical fibers run. The interesting concept here is that they take 2 signals out of out of the detector. One is they detect the scintillation light coming from energy deposits. The other one is the Cherenkov light. Cherenkov radiation is given out by relativistically moving particles in a medium. When their speed exceeds the speed of light, they emit a cone of light, which is very similar to the shockwave sound cone that a supersonic jet makes in front of its nose. So fast particles make a cone of light like that. These rings of light can be detected, and they detect this Cherenkov light. Now, the Cherenkov light comes mainly from the electromagnetic component of the hadron shower. And that's how they estimate the electromagnetic component and improve upon resolution. So the summary is in the next slide. The summary of energy resolution is that you can achieve 3% accuracy for electromagnetic homogeneous calorimeter, 10% for sampling calorimeter. For hadron calorimeter, if it is a non-compensating calorimeter, it is 50 to 100%. And if it's a compensating calorimeter, it's 35%. And the dream is to go to 15%. So I have slides. I'm already 15 minutes over. I have slides on accuracy of position measurement and time measurement of calorimeters. Let me skip those slides unless there is a question. Let me just mention that calorimeters can measure position within millimeters of accuracy, and they can measure time of impact within hundreds of picoseconds of accuracy. And future calorimeters are trying to do it within tens of picoseconds of accuracy. Now, let me go to slide number 52. Yes. So I have to say a word on this before closing. So all these calorimetry concepts combined can make the best of the detector when they are combined with information from other parts of the detector. For example, the right top picture shows a CMS picture of an electron, of a photon, which converted into E plus E minus in the tracker, and then that E plus E minus shown by yellow lines, you can see conv brane tracks. They are bending in the tracker. While they're bending, they're spraying out photons. Those photons are hitting the electromagnetic calorimeter shown in the green lines. And the original electron coming out of the collision also bends in the tracker shown in the light blue line. And that also hits the electromagnetic calorimeter and deposits energy. So one needs to combine all of this information to get the best energy momentum measurement. And that is done with an amazing algorithm in CMS known as the particle flow algorithm. 3 or 4 people, great experts in CMS, spent 4 years of their life developing this algorithm. And without this, CMS would have been a lot less accurate detector. I just wanted to mention that. So the particle flow is a great thing that we have. Next slide, just in one word, we have improved our accuracy of measurement of energy of hadrons with this algorithm. The hadron jet energy accuracy is shown in the right plot here in the yellow band as a function of momentum of the jet. And Then the next plot, let me spend 1 minute on this. And so this is these two plots are of extreme importance to a high energy detector. The right plot, the left plot, shows it essentially shows the negative of the vector sum of the three momentum of all particles that have been detected in the detector. So this is supposed to be zero because the incoming momentum was zero. Two protons colliding head-on from opposite directions. Now, if this is not zero, that means something was produced which has taken away momentum undetected. This is known as missing transverse energy, or MET. It's essentially missing momentum. And the plot on the left shows how well our detector simulation matches with the true measured momentum imbalance. This is important because suppose in proton-proton collision, dark matter particles are produced. A pair of dark matter particles are produced, which is a research interest of mine. These are weakly interacting particles. WIMPs are weakly interacting massive particles. They will escape the detector without depositing in any energy. So they will give rise to missing transverse momentum. And supersymmetry is a theory, is a beautiful theory which predicts the existence of such dark matter candidate particles. It is to find supersymmetry is one of the major programs of LHC physics. So those physics will be discovered from the measurement of missing transverse momentum. And this plot shows how well we do in measurement of missing transverse momentum, thanks to our calorimeters and to particle flow. So next slide. I wanted to talk about this detector. This is our future calorimeter, and I'm involved in this, but in interest of time, let me skip or almost skip. Let me go to the next slide and just very quickly say that by 2025, we will replace our low angle calorimetry with a new 3D imaging tracking calorimeter. And for the first time, this will be a calorimeter which can also do tracking. And it's a calorimeter which has silicon sensor layers inside it. So the top left picture is one such silicon sensor module with fully loaded electronics. This particular module we made in India by taking the design from Minnesota. It was made in a company in Hyderabad, and this is a project of SINP. And the bottom pictures show simulation done by my student of what happens to a muon and what happens to a pion when they go through such detector modules. We are also working, people are also working for doing 3D imaging of particles using modern machine learning complex concepts like graphs and graph neural networks. So it's all very interesting. I cannot cover it here. Instead, let me come to the conclusion of this talk with two slides from where I started. So 1964, 3 different papers in the same volume of physical review letters predicted the existence of a new particle. This is the first page of one of those papers written by a physicist by the name of Peter W. Higgs, published on 19th of October 1964. In the second page of this 2-page paper, he predicted, he had one line which says that quanta of a spin zero field, which can explain the mass of the massive W boson and Z boson, should exist. And then from 1964, high energy experiments have looked for this this treasure called the Higgs boson. Next slide. And around 2010, in our detectors, this is a picture of electromagnetic calorimeter of the CMS. We started seeing events with two photons coming out with a lot of energy, hitting two cells of the electromagnetic calorimeter. When their energy and momentum position was measured, and we calculated back the mass of the particle from which this may be coming, what we saw is in the next slide. And what the CMS and at the same time the ATLAS experiment saw is that in the spectrum of the mass of the diphoton system, there is a peak around 125 GeV, and that's the discovery of Higgs boson. This was possible due to modern day electromagnetic and hadronic calorimetry, along with very sophisticated algorithm like the particle flow algorithm. And we are looking forward to the future of calorimetry to discover particles like dark matter particles or supersymmetry. None is yielding so far. So with that, I will end this lecture. I wish that I could visit in person your institute and give the talk there, but I have visited in my imagination, and I have also in my imagination compared the size of the CMS detector with the central building, and I think it's in height it will be comparable with the building, and in radius also. So with this, I'd like to thank you for giving me the opportunity to give this talk. Sorry for exceeding the time, and I should stop here.
Thanks a lot, Professor, for such a wonderful and elaborate talk. With your kind permission now, I would like to request participants to ask a few questions directly. If anybody have any question. Anyone have any question? Oh. Okay, so thank you so much.
There is one question in chat box, Nadi.
Okay. Here's a question. In computing respects, can the steps of energy reconstruct by simulate in softwares for the study and analyze of the signal pulse? If so, are the data sets available on open source for doing so?
The short answer is yes to both questions. I have a master's researcher who is accessing CMS open data and trying to analyze the simulated data. So anyone can use the open data.
Is there, there's another question. Is there any possibility of existence of particle even fundamental than quarks and leptons? Are we theoretically forbidden to talk about this?
Okay, so in principle, yes. As we go to higher and higher energy, actually we are looking at smaller and smaller length scale, and what appears to be fundamental today may appear to have substructure tomorrow. But so far, so the LHC energy of tens of TeV converted into length, remember that length times energy is a dimensionless quantity. It appears in the wave equation of quantum mechanics, we have the e to the power I p times x. So p times x divided by h cut is a dimensionless quantity. So every energy dimension can be converted into a length dimension. So LHC probes the universe at a length scale of 10 to the power minus 17 to minus 18 meters. At this length scale, there is nothing more fundamental than the quarks and leptons.
Any further question? Okay,
Hello, sir. No, I have a question.
Yes,
Hello?
Ruchi, you can ask.
Yes, sir. I don't remember the number of slide, but I think it was about the missing energy, right? That met slide. Sir, do you remember? Hello?
Yes, so that's slide number 54.
Yeah, maybe that's so. In that one, can you please repeat the reference you were saying that time? Like, is it related to the calibration system? Can it be measured? How is it exactly measured?
Okay, so let's take a simple event, the Higgs decaying to 2 photon event. Now, what are the final state particles? Just 2 photons. So we have a reaction, proton coming in and 2 photons coming out. Now I can measure the momentum of both the photons, the 3 momentum of both the photons. I can take their projection on the XY plane, which is the plane perpendicular to the beam axis. Then I can vectorially add these two. After adding these two, what do I expect? I expect that their vectorial sum should be 0. Because to start with, there was no momentum along the transverse direction. The beams were along the horizontal axis. But now, if I see that the vectorial sum, the magnitude of the vectorial sum is 100 GeV, what will I conclude?
That there is something there, but it is not visible.
Yes. So there is something there which is also 100 GeV and pointing exactly opposite to the direction of this momentum vector. So a large unbalanced momentum vector is a sign of an invisible particle being produced. Does that answer your question?
Yes, sir, but I was asking one more thing. Is it
Okay.
somehow related with the calibration?
Yes, it's so MET measurement is probably one of the most difficult measurements that we have. Of course, it's related to the calibration. It's related to the calibration of the electromagnetic calorimeter and hadron calorimeter. If we miscalibrate our energy measurement of the hadrons, then we can generate spurious missing transverse momentum, which is just our mistake. So, and this happens in every event. There is always spurious source of energy or missing momentum due to calibration problems, but also another source of spurious missing transverse momentum is gaps and cracks inside the detectors through which the particles can escape.
Yes, sir. Thank you.
Okay, is there any further question? Okay. There's a question, how will we determine whether the momentum imbalance due to neutrino or dark matter?
Okay, good question. There is no way to know. So if you see that there is missing transverse momentum, we would not know whether it's coming from a neutrino or whether it's coming from dark matter. But one thing we know very well starting from 1974, in all these years, we have learned that standard model works like magic. So, and standard model is highly precisely measured. Neutrino is a standard model particle. So we know all the sources of neutrino. So we can, this is what is called background simulation. We can simulate all the known sources of neutrino, and we can estimate that how much missing transverse momentum can come from neutrinos. And then if we see an excess in the events with missing transverse momentum over and above what is expected from neutrinos, from detector imperfections, then we know that we have made a discovery.
Okay, thank you so much, sir. Here we will end our question session, and like you, we are also looking forward to have you with us sometime here in future at NIT Jalandhar. And once again, on the behalf of the Department of Physics, NIT Jalandhar, we are very thankful to you for taking out time from your busy schedule. Thank you so much, sir.
Thank you indeed.
Okay, now I would request
inviting me.
Sunil sir if he wants to say something to you.
Sure. Actually, I would like to thank Professor Satyaki for all his time on behalf of all of us. And he has not only been a great friend to me, but also a sort of role model to me as well. And I'm thankful to you once again, sir.
Thank you, Sunil.
Thank you, sir.
so much,
Thank you
sir.
very much.
Now, here, dear participants, we will meet you in our next session tomorrow. Thank you for being a wonderful audience. Goodbye.
Bye.
Bye,
Bye, sir. Bye.
Bye, sir.